All right. Now that we've talked about magnetic forces and the effect that the magnetic field has on moving particles, now we're actually going to zoom out and talk about where these magnetic fields come from. And the answer is that static magnetic fields simply come from moving charges. And the easiest way to get a source of moving charges is, of course, a current. So we'll usually look at B fields from current carrying wires. And the defining feature of these magnetic fields were that they form closed loops. So to actually figure out the direction of the magnetic field due to a current carrying wire, we know they form closed loops, and more specifically, they form circles around these wires. And you can find the direction that they circulate by using your hand, because if you stick your thumb in the direction of current, which is again positive charge flow, because we use conventional current, your fingers will sweep in the direction of circulation. So we see here that we get sort of this counterclockwise spinning around this current towards the top of the page. And there's nothing special about it being a current source. Single charges could also generate magnetic fields. And it's easy if it's a positive charge because you can just pretend it's a wire. But we have to remember that for negative charges move in the opposite direction as current flow due to that conventional current being positive charge flow. So if you ever have a negative charge, you can just pretend it's a wire with current going the opposite way. So there's two common orientations of wires you'll see. So first, if your wire is entirely in the XY plane, carrying current, that means your B field is going to be popping into and out of the page. So again, here, if I stick my thumb to the right, representing that current, notice that my fingers are going to pop out of the page when I'm above the wire, and they're going to curl back into the page when I'm below. And we'll see that it actually decreases, this field actually decreases in magnitude as you get farther from the wire, which is why we started from large circles and large X's to small circles and small X's. It's much easier to see the circles if you actually have a wire that's carrying current perpendicular to the plane that you're looking at. So again, to do these, you sort of stick your thumb at you, and then you wrap your fingers accordingly. So here we see that we do get a counterclockwise sort of sweeping effect here. All right, so let's do some drawing. Draw the magnetic field generated by each of the following currents. So here we got current towards the top of the page, so I can stick my thumb towards the top of the page, and notice if I sweep my fingers are going to point at me when I'm to the left of the wire, and they're going to point away from me when I'm on the right side of the wire. So we get a field that's out of the page on the left and into the page on the right. So again, you look at if your fingers are going at you or if they're going away from you. All right, now we have a wire, and again, that X means it's carrying current into the page. So we'll draw ourselves a nice little circle here. That looks to be centered enough for government work. No, we'll nudge it. We'll nudge it a little bit. Good enough. So we know we're going to circulate. So how do we circulate? Well, I take my thumb and I stick it in the direction of current flow. And if we do that, notice I get a clockwise sweeping. So we can just draw a couple arrows that sort of show that we get this sort of counterclockwise sweeping. Notice that this B field is going to be tangent to our circle at all points. And that's actually useful later on when we look at something known as Ampere's law that helps us calculate these fields. So we get a counterclockwise circulation here. All right, C. Well, C, this is just a positive point charge moving towards the bottom of the page. So since it's a positive charge, we can just model this as a current towards the bottom of the page. So we'll pretend that you are a wire carrying a downward current. Not the best wire I could have drawn in the world, but whatever. So we're really just saying that there is a current going down. So I is actually down. So if we do that, I stick my thumb down and notice that when I'm to the left of the wire, my fingers point at me. And when I'm to the right of the wire, or sorry, they point into the screen when I'm to the left, and then they come out of the screen when I'm to the right. So we get this. Because again, notice that if you circulate, again, you know it's going to circulate like this. So I stick my thumb down, and then notice that my fingers point into the screen when I'm to the left of the wire, and they point out of the screen when I'm to the right side, because they sweep out. Negative charge. Well, of course, a negative charge. You are like a current, except current is positive charge flow. So we can just model this as a current in the opposite direction. So we can actually say this is a leftward current. And we do the same thing. Use my right hand and notice my fingers go into the screen when I'm above the wire. And then they pop out, back out when I'm below. So there's our fields. Now we'll do some rankings. So we have all these different arrangements of wires that are separated by the same distances, and they carry the same currents. So some of them are into the plane, some of them are out of the plane, but they're all the same current magnitude. And we want to find the magnitude of the net field at the midpoint of the two wires, so right between them. So of course, we're just going to do some addition / subtraction here. So let's draw our arrows first. So we'll do the left wires here. All right, so into the page means we're going to circulate clockwise. So I'm just showing that on this side, we get a downward field there. Same idea, we also circulate clockwise around this one. So we get fields that point up. So we can already see what will happen in this case, that our net B field is going to be effectively 0, because the up arrow and down arrow exactly cancel. What about B? Well, B, similar idea, right? We have a circulation. This one is going to be counterclockwise. And then this second wire is identical to the previous case, so this will also be up. So what we see, we're just going to get two arrows of equal magnitude adding to each other, so we're going to say that net field is 2. All right, going down to C. So for C, notice if we use our right hand, I stick my thumb up. The field comes at me to the left side of the wire, but it goes into the screen here. So this would be an into the page field on this side. And then similarly up here, if I stick my thumb up, my fingers come at me when I'm on the left side, and then they point into the page on the right. So this is coming at me, so that's out of the page. And even though it's in the Z direction, we can see we're still going to cancel out here, right? Because I got out and in perfectly canceling, so this is also 0. And then the interesting one is we got case D, where we know you are going to be a counterclockwise circulation. Circulates counterclockwise. And then our wire up here, stick my thumb up, and my fingers come at me on that side. So what is this? Well, we know it's going to be greater than 1 because they don't cancel each other. But it also can't be 2, because that would be if they perfectly add. But if we think about it, this arrow is in the Y direction, and this arrow is in the Z direction. So we actually form a right triangle. So we're really just adding 1 plus 1, except it's a Pythagorean theorem idea. Because we're really just sort of adding, we're finding the magnitude of J hat plus K hat is what we're really doing. And those are unit vectors that are perpendicular. So we can use the Pythagorean theorem. So we get 1 plus 1, but in the Pythagorean theorem world, so that's actually square root 2. So not 2, but it's square root 2. All right, so we can rank this. So we see there's a two-way tie because there's 2 of the cases that actually cancel. So we'll spoil that later. So A and C are equal because they canceled each other. Then at D, we had the square root 2. And then at B, we had the 2. So our justification would be these effectively have 0 field. This has square root 2 field, and this has 2 field. Because here we had perfect cancellation, here we had perfect addition, and then in the middle we had that Pythagorean addition. So we can see that at points A and C, equal and opposite, 0 net field. At point B, same direction, perfect addition. At point D, the fields add via vector addition, but it's not quite double because they're not in the same direction. It's going to be perpendicular, so we have to use the Pythagorean theorem. So pretty straightforward ranking there. We will derive this formula later, but the magnetic field from a wire is equal to mu naught times I over 2 pi r. So mu naught, this is a constant called the permeability of free space, or vacuum permeability, which represents roughly a material's ability to magnetize. So this has a value of 4 pi times 10 to the minus 7th Newton per ampere squared, so that's your SI unit there. I is, of course, the current, and R is the perpendicular distance from the wire. So in this class, we're going to assume that our wires are very long, unless told otherwise, so that we can use this formula. If it wasn't infinitely long, you'd have to use some more calculus ideas, and you get a nastier looking formula. And because you can prove it with calculus, this is actually not on the APC formula sheet, but it is on the AP2 formula sheet. So this is an equation that you absolutely should memorize. And also, notice that you get some interesting effects here because, of course, it makes sense that B depends on I, because if we said it's moving charges that generate B fields, makes sense that I is involved. But also, there's circulating, so it makes sense there's a 2 pi r involved. So it does actually fall off with distance, but it's 1 over r instead of 1 over r squared, like you'd get for like a point charge with an electric field. All right, let's do an example. A long wire is carrying a current of 2 amps to the right. Indicate the direction of the field 0.2 meters below the wire. All right, well, right hand rule. My fingers pop out of the page above the wire and then they wrap into the page. So this is going to be into the page. I guess I didn't write it down. Into the page. Just using the right hand rule. Now we'll calculate it. So the magnetic field from a wire is defined as mu naught I over 2 pi r, and we know all of these things. So mu naught, this is a constant, it is known. It is 4 pi times 10 to the minus 7th. Our current was 2 amps, and our distance we're taking the field at is 0.2 meters. So if we do that, notice the pi's go away, the 2's go away, so I'd essentially get 4 times 5, which is 20. I'd get 20 times 10 to the minus 7th, which is 2 times 10 to the minus 6 Tesla, also known as 2 micro Tesla. So maybe we'll put that over here somewhere. Now we'll calculate with direction the force experienced by a 5 microcoulomb charge with positive charge traveling at 10 to the 6th meters per second to the right at this point. So why that's helpful to us is because if we have a moving charge, and it's moving towards a magnetic field, well, we actually know how to do this. This is the right-hand rule, or the Lorentz force law. So we know that the magnitude of the magnetic force is QVB, as long as we're taking V to be perpendicular to B. No issues here. Q is 5 microcoulombs. V is 10 to the 6th. And B is 2 times 10 to the minus 6. So if we do that, the magnitude of the magnetic force is going to be, well, these cancel. So we get 1 times 10 to the minus fifth. So we get 10 to the negative fifth newtons. But we also do want the direction, so remember we can figure that out because QV, right? We use QV cross B. So QV, V, your thumb, right thumb, because we're using a positive charge, cross B, stick my fingers into the page, and notice my palm pushes up. So this means that the magnetic force is 10 to the negative 5 newtons up, also known as towards the wire. And we'll see this is actually a special case of a more general fact that like currents attract, which is not how it works for charges. But we get an interesting attraction rule that like currents attract each other. Because again, if it's a positive charge, you're essentially a wire that's carrying rightward current. All right, so now we're going to do some superposition with wires and do a nice little ranking. So we got 2 long wires, and all these points are a distance d from the nearest wire. So for example, this distance is d, this distance is d, this distance is d, and so on. It'll just make it easier for us to count distances that way. And we're going to rank the B field at each of these 3 points. Then we're going to derive an expression, make sure everything's all consistent and as expected, you know the drill. All right, so first, we have our first wire. So if I do my right hand rule, my fingers are going to point at me on the left side, and they're going to point away from me or into the page on the right side. So I'm going to give 1 circle there, 1 X there, and then I'm going to put a smaller X there because we know it decreases with distance. So A and B are equal lengths away from the wire, so I drew those the same size, but I drew a little small one at C. Okay. Now let's do our other wire. So our other wire, our 2I, it's a current 2I, so it's going to be bigger. So for direction, we see that it's going to point at me to the left and away from me to the right. So we'll go right to left this time. So since it's 2I, I'm actually going to draw sort of 2 contributions there each time now. So we actually know this is going to be into the page, we said. So I'm going to draw 2 into the page symbols right there. Then we know it's out of the page on the other side, so I'm going to draw 2 out of the page symbols at B. We'll center that. And then we have 2 more out of the page symbols at A, but those are going to be tiny. Okay, so this is actually enough information to tell us what the fields add to. So notice first that the lowest is going to be B, because these 2 cancel, and I'm just left with a normal sized circle. Whereas at A, I have a normal sized circle and 2 little ones. And at B, I have a little circle and little x and 2 normal sized ones. So actually, we know that B is going to be less than each of those because of the subtraction that's happening at B, whereas there's addition happening at A and C. And we also know that C is actually going to be A because C is closer to the larger current source. So instead of adding 1 big circle and 2 little ones, we're adding 2 big circles and 2 big X's and 1 little one. So we get lowest strength is at B, then intermediate is A, and then highest is C. So our ranking, I would say the fields add at A and C, but subtract at B. The magnetic field beats A at the magnetic field at C beats A because C is closer to the larger current source. So yeah, it's true that they add at both A and C, but the currents aren't equal. So if you're closer to the stronger current, that's going to beat the field. All right, let's get ourselves some field strengths. So at A, this is going to be true for all of them, by the way. So we're going to do our daily shameless copy paste. Our net B field is going to be B from the I wire plus B from the 2I wire. So shameless copy paste incoming, copy paste, and paste again. There we go. All right, so let's deal with that here. So for A, point A is D away from the left wire, and it is 1, 2, 3 D's away from the 2I wire. So we can write mu naught I over 2 pi D from the I wire, and that field was going to be directed out of the page. And then we get mu naught times 2I over 2 pi times 3D, and that's going to be directed also out of the page. So notice we can see our little interpretation here where this was our blue circle, and this was our 2 tiny purple circles. So if we do that, we get 1/2 is like the number in front of the mu naught I over 2 pi D. So we get 1/2 here, and we get 1/3 here, and those add 1/2 and 1/3. So 1/2 is 3/6. 1/3 is 2/6. So we get 5/6 mu naught I over pi D. And this does have a direction, so it is out of the page because we get circle plus circle, which is of course going to be circle. 5/6 mu naught I over pi D. And allegedly this should be in the middle. This was like our middle ranking because the field's added, but we could do better. All right, what about the middle? BB. Well, it's a distance D from the left wire. It's a distance D from the right wire. So we can just go ahead and plug that in. So from the left wire, it's going to be mu naught I over 2 pi D. This one was into the page, and then we get mu naught I, well, with the 2I at least, mu naught 2I over 2 pi D out. So we see why it only partially cancels here, because again, this represents our into the page field, so we got a large circle there. But here we had our two large circles to cancel the one large X, and we get exactly 1/2 as our multiplier, right? We get 1/2 and then minus 1, so we get 1/2 mu naught I over pi D, and this one is actually into, nope, it's also out of the page. We can write it right, we can draw it right, but I'll still say it wrong every time. And then so this should be the weakest. And then for C, well, for C, for the I wire, point C is 1, 2, 3 D's away, and the 2I wire is just 1 D away. And both fields are into the screen. So we get mu naught I over 2 pi times 3D, and that was out, no, in. And then we get mu naught times 3I, no, not 3I, I'm so silly, 2I over 2 pi times 1D, and that's also in. So we get 1/6 plus 1, which is 6/6. So 6/6 and 1/6 makes, 7/6 mu naught I over pi D. And this is into the page. All right, so let's compare. We said that the weakest field was at B. Makes sense. We got 1/2. Then was A. Makes sense. We got 5/6. And then at C, that's the greatest. We got 7/6. So everything looks fine here. What's the direction of the magnetic field at B? Justify your answer without referencing equations. Oh, I just wanted magnitude. Well, isn't that lovely? We did extra work. Well, clearly it is out of the page because the B field generated by the bigger wire at point B is out of the page. So yes, there's some canceling, but we know that since the 2I wire has a greater current and the distances are the same, its field will end up winning. So essentially that. The wires generate fields in opposite directions, and this is out of the page, by the way. I'm lying. The net magnetic field is out of the page. I forgot to change that. The wires generate fields in opposite directions and are the same distance from point B, so the net field just points in the direction of the field generated by the wire with more current. So again, we just see that since the 2I wire has larger current and it's generating a field out of the page at B, we know that's the one that's going to win. My old solutions are trying to gaslight me into thinking I did it wrong, but it's definitely right. All right, let's do some angled versions of this now. Two wires carry currents perpendicular to the page. They're placed at opposite corners of a square. Draw the direction of the net magnetic field at the bottom right corner without manipulating equations. Well, what do we know about B from a wire? B from a wire circulates. So let's think about it. Well, if I point at me, this is going to be counterclockwise. So I'm going to say that we get effectively 3 contributions up from the 3I wire. Then for the 4, and I'm sure you can guess where this is going. Whatever could possibly be happening if I have a 3 and a 4 at right angles. Well, we know that the 4, you're generating your current is into the page, so you're going to sweep clockwise. So you're essentially giving 4 magnetic field units to the left. So we effectively have 4 horizontal pushes and 3 vertical pushes. So we're going to get something like this, where we get B from the 4I, then we get B from the 3I, and then our B net, of course, is going to be the slant. So we do know that it's going to be up and to the left, and we actually can go a step further than that. So this doesn't make you just pick the quadrant, it makes you pick which component is bigger. And notice that it's going to be in this octant. Yeah, octant. Man, I can't draw my right line tool today. It's going to be in this octant. Don't care where, but we know it's going to be in that octant because this represents having more horizontal than vertical. So the magnetic field from the 3I is up, the 4I is left, but the 4I beats the 3I, so we know the field is going to be pushed more left than up. What is the net magnetic field at the bottom right corner? Well, we've already done a lot of the scaffolding. We already know kind of the outline, right? Because we know that the bottom right corner, we have B from the 4I. That's going to do something. We have B from the 3I. That's going to do something. And then the net field that we want is, of course, our slant length. So now we can turn this into a triangle because we know that B from a wire is equal to mu naught I over 2 pi s. So the only thing that's changing, we know that the distance is going to be s each time because we're along a square, but the current is either 3I or 4I. So we can just rewrite our triangle as the horizontal leg is going to be 4 mu naught I over 2 pi s. The vertical upwards leg is 3 times mu naught I over 2 pi s. And you've probably predicted it coming for a while, what the hypotenuse is going to be of this. But Of course, we'll find it because that's what we do. So B net is equal to, we know the units are mu naught I over 2 pi s. And then we just use the Pythagorean theorem, 3 squared plus 4 squared. Wow, it's a 3, 4, 5 triangle. Who would have guessed? So we get 5 mu naught I over 2 pi s, which would be the equivalent field of a wire of current 5I placed at one of the corners, or placed at one of those vertices. Cool. What will happen to the previous two parts? So one part A was the direction, and part B was the magnitude. If we change both current directions, keeping the magnitude the same. Well, if you change both current directions, you're going to flip both arrows. So instead of 3 up arrows, you get 3 down arrows. And instead of 4 left arrows, you get 4 right arrows. So that's, of course, just going to flip everything backwards 180 degrees. So if I flip both directions, this arrow is just going to invert 180 degrees. So the direction will be reversed. So it's rotated 180 degrees, exactly opposite. But the fields are still perpendicular, right? Left plus up has the same magnitude as right plus down. So Pythagorean theorem still works, so nothing changes with the magnitude. It just faces the exact other way. That's a nifty little Pythagorean theorem one. And now to conclude, we have one that can be a bit annoying to track our trigonometry angles around, but it's a useful exercise. So this helps us actually draw magnetic fields because we know that the magnetic field forms a circle. So it's really easy if you're at like a 12 o'clock position or something like that. But if not, you have to draw a radius line to your point of interest and then draw a perpendicular to that to show the tangent or the circulation. So let's try that. So our first wire up here, if we're interested in that, we're going to be looking at the magnetic field sort of along the perpendicular bisector of these two wires. So I drew myself a little radius vector because that's going to show me my circle. So if I really wanted to, I could have drawn myself like a big old circle centered there. I know that's not a great example, but this at least shows me what I'm doing. So remember that current, or the B field circulates around current. So since my current points at me, it's going to circulate counterclockwise. So if I imagine drawing myself a nice big circle around this thing, it's going to point counterclockwise. So the first B field would point this way. Alrighty. So now we'll move this and do our other vector. So our other wire, similar idea. Now if I drew a circle for this one, it's also going to circulate counterclockwise. So I could draw myself a nice big circle there, and that's going to circulate counterclockwise. So we can see what's going to happen here. This is also going to point sort of like this. So if we look at what happens for our net magnetic field, and I could have done a better job, we see that we get some canceling that's going to happen due to symmetry. So if we drew this out, we'd see that the left and right components cancel, and the vertical components are going to add. So what's our net B field? Well, our net B field is going to be up. Top wire generates a counterclockwise field, up and right. Bottom wire generates a counterclockwise field, up and left. By symmetry, the horizontal components cancel, leaving a net upwards field. Because again, we're essentially saying that up and right was our first vector, plus up and left, which was our second vector, yields a net magnetic field directly up when we tip to tail that. So derive an expression for the net magnetic field as a function of x, this coordinate along the axis. Okay, so here's where we have to be a bit creative. So I'm going to redraw this. I'm just going to draw one of the wires, and we can just use some symmetry there. So I'm going to draw one wire, and I'll draw my sort of radius vector there. And we also know that the magnetic field from this wire looks like this. Okay. And this is a right angle, which comes into play later. So what do we want? Well, what we know is that it said it's placed along the y-axis at y equals a. So this distance was a. This distance is x. So we can, of course, get our missing side length of this triangle using the Pythagorean theorem. That annoys me. I like to write the variable first. Not that that matters. Okay? But this is the magnetic field. So we said the magnetic field, the only one that actually contributes is the vertical component. So what I need is I need to break this vector apart into its y component. So what I'm interested in is this by, which is equal to b times sine theta. And actually, I have to remember that there's two wires, so I'm going to have to double this there too. So this would be b from one wire. So we're going to have to do some angle tracing in a minute, but let's just start there. We know that the net magnetic field is equal to 2 times the y component of one wire's magnetic field. So now we'll have to do some angle tracing, because we also know this is equal to 2 times b times sine theta. So where does theta go? Well, notice that this makes 180 degrees. This arc right here makes 180 degrees. So I have theta 90 degrees and a third angle that makes 180. See that semicircle there? Well, this must mean that this angle down here is actually 90 degrees minus theta, because that's the only way I can get this entire arc to add up to 180. And just check it, it works. So that must mean that theta actually goes up here in the other triangle. And I'm sure there's some alternate interior shenanigans you can pull to make this a bit easier, but that's how I saw it, at least. So that's why it's key to actually know that the magnetic field makes this right angle with the radius vector there. Alrighty. So we can just substitute. So we know what b is from a wire. B is mu naught I over 2 pi r, but r is going to be that Pythagorean distance, and sine theta is going to be, well, an opposite divided by hypotenuse, right? So ka toa. So opposite would be x, which doesn't touch, and the hypotenuse, x squared plus a squared. So if we work out our magnetic field, we see that the 2 cancels with the denominator, and the square and square root actually cancel. So we're just left with mu naught times 9, ix, Roman numerals, times pi times the quantity x squared plus a squared. We do actually know this net field is up as well, so we could actually say that. By evaluating your expression at x equals 0, verify the magnetic field is 0 at the origin, justify why this is true. Well, first of all, it's easier just to plug in and check, right? B, when x equals 0, is just going to be mu naught times I times 0 divided by pi times 0 squared plus a squared. Denominator's not 0, so I'm totally good with just calling this 0. So why is this expected? Well, what does it mean to be at x equals 0? Well, if you're at x equals 0, you're right here. This is x equals 0, so you're right between the 2 wires. And if you're right between the 2 wires, that looks like this. So we'd get counterclockwise here, and we'd get counterclockwise here and counterclockwise here. And notice you'd exactly get our expected result of fields cancel right at the center, right? Because we have a left and a right. So When x equals 0, the point is between the two wires, which causes the fields to exactly cancel, so of course we get 0 field. So that's a little geometry extension there, a bit of angle tracing, bit beyond what I really like, but a cool problem nonetheless. And I like our little limiting case here. So that's all of our things we can do with the B that we can create with a wire by itself before we incorporate forces.